All right, it's time to go over more free responses with your pal, John Frensley. This video is brought to you as a public service by World's Finest Physics. I'd like to tell you a little bit about our professional development sessions coming up. First of all, one for physics teachers. If you're watching this might be interesting to you. It's July 24th to 27th in Frisco, Texas. It's in person. We're going to do a bunch of different mechanics topics, and we're really going to focus on hands-on activities. Could be AP Physics 1 or AP Physics C, but it could also be those who teach college or pre-AP or regular honors. Any of these topics right here, and anyone who wants to you know, boost the level of inquiry in your physics class, the level of engagement, make the class more fun, lots of hands on activities, ways to improve writing, ways to tackle difficult concepts like Newton's third law, lots of stuff like that. You're also welcome to advertise my professional development session for math teachers to the math teachers at your campus. It's the week before, and we're going to increase student engagement with, you guessed it, a whole bunch of hands on activities, math games that I've invented, scientific method. So, the better your math teachers do, the better your students do when they get to you in physics. So, this could be something you want to advertise your math teachers. And if you're a student or parent and you happen to be seeing this, we also provide private tutoring to students in these subject areas right here. All right. So if you want to reach out, findphysics.com, either look at the uh, 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 session agenda for the physics teacher session, the math teacher session, or if you just want some extra help, findphysics.com is where you want to go. All right, let's see. Let's not forget our acknowledgments to the College Board for coming up with these wonderful questions right here. And in general, just being a beacon of professionalism, whether it's, making a major change to AP Physics 1 curriculum and then informing everybody in a parenthetical comment on an email on Friday afternoon when everybody's gone home for Christmas break, or just suddenly canceling the SAT too, just without really telling anybody. Uh, your professionalism deserves commendation or maybe condemnation. I don't know. As far as I'm concerned, your professionalism makes Donald Trump look like Jean-Luc Picard. And then Golden Corral, their food is about as real as the College Board's principles, and they use the same logo font as College Board. Isn't that great? All right, so here we go. This is AP Physics 1. Cart is on a horizontal surface attached to a spring. The other end of the spring is attached to a wall. The cart is initially held at rest, shown in figure 1. The cart's release systems consists of the cart and spring oscillates between L and negative L. Figure 2 shows a kinetic energy as a function of potential energy, which makes sense because K plus U equals E. It's kind of like X plus Y equals a constant, so that would be a line with a slope of -1. On the graph of kinetic energy in figure 2, values of the X and Y intercept are the same. Explain why this is true. Okay, so the y-intercept is the kinetic energy when all the energy is kinetic energy, right? The x-intercept is the potential energy when all the energy is potential energy. So what am I thinking? I'm thinking since energy is conserved. All right, since energy is conserved, I'm going to underline that because it says using physics principles, right? Since energy is conserved, the the uh, uh, the maximum kinetic energy and maximum potential energy are equal. Okay, so there you go. It's pretty straightforward. All right, so now when the cart is at x equals positive L momentarily at rest, a block is dropped onto the cart, shown in figure 3. The block sticks to the cart, and the block cart spring system continues to oscillate between that. The mass of the cart and the block are m naught and 3m naught respectively. This sure reminds me of a problem that I wrote for National Math and Science Initiative. I did not send that problem to the College Board, so I have to wonder if somebody might have seen that problem I wrote, about 7 years ago for the National Math and Science Initiative and might have gotten some inspiration from it. Anyway, The frequency of oscillation is F1. The frequency after the block is dropped is F2. What's that ratio? Okay, now if you saw the mechanics video, I made a lot of mistakes in the mechanics video. So I did actually have a look at these questions a little bit in advance. It was at my son's soccer game. It popped up on my phone that they had been posted. And so, of course, rather than watching him score a couple of goals for the first time ever, I'm looking at these questions, kind of thinking about them. So I haven't written anything out yet, but I've thought about them beforehand, right? Okay, so period equals, let's get this one right compared to the mechanics video, 2 pi radical m over k. Now, it looks like you go from m naught to 4m naught. So this gets multiplied by 4, which means the period gets multiplied by 2. But here's the thing, is that period and frequency are reciprocals. So frequency is reciprocal of period. So the period doubles and the frequency is divided by 2. So then this is half as much. So I'm going to say calculate numerical value. The value is 1/2. And then I'm going to kind of write out what I'm thinking here. Since the mass is multiplied by 4, the period is multiplied by 2. Since period is 1 over frequency, if period is multiplied by 2, then frequency is multiplied by half or something like that, right? Okay, wow, was this entire page just for this? Wow, College Board, you love the trees, don't you? Okay, here we go. Kinetic plus potential energy, the block frame card system after the block is dropped on the cart, and you'll notice it's the exact same energy. It would not be the exact same energy if you drop the block at the equilibrium or anywhere else, but because you drop the block at the endpoint, then it's a sticky collision between an object with zero velocity and an object with zero velocity. Normally, sticky collisions will dissipate energy, but not this time because the objects have zero velocity before and after the sticky collision. So you actually get to keep all of your energy. And the reason I know that is because I wrote a problem like this for the National Math and Science Initiative 7 years ago. Okay. Um, so the graph is identical to, okay. Briefly explain why the two graphs must be the same using physics principles. Okay. Well, I'm just going to say this. I'm going to say, um, uh, before the block is dropped. Okay, so before the block is dropped, all the energy is potential energy, which is 1/2 KL squared. Now remember, it's 1/2 KX squared, but because the amplitude is L or the displacement is L, then it's going to be 1/2 KL squared. This is also the potential energy after the drop. Well, it says briefly. So when it says briefly, it usually means you can get it in one sentence, but I don't know exactly what they want to hear. So it's going to be a couple, maybe 3 sentences here, even though it's crammed to this inch of space. There's also the potential energy after the drop. Um, so the total energy is the same before and after the drop or something like that. So the bottom line is that the reason that a sticky collision dissipates energy is because there's kinetic energy to be dissipated. But there's no kinetic energy here during this sticky collision. So there's no kinetic energy to dissipate, right? So when you have, I know it's called perfectly inelastic. I'm going to call it sticky collisions to deal with that. So sticky collision dissipates only kinetic energy, but since there's no kinetic energy before or after, why? Because the cart and the block are both at rest, and they're at rest both before and after the collision in this case, then you don't have any kinetic energy to dissipate. Now, after the block is dropped onto the cart, consider the system that's only the cart and the spring. On figure 4, sketch a solid line that shows the kinetic energy of the system that consists of this cart and the spring. Now, I did rehearse this in advance, so I think I'm going to get this right. Originally, I was going to draw a little line here because I was going to say, well, the cart is 1/4 of the mass, right? If the cart's 1/4 of the mass, kinetic energy equals 1/2 mv squared. So I was like, well, if you have 1/4 as much mass, you have 1/4 as much kinetic energy. So I was just going to draw a line from 1 to 1, and then I forgot. And then I remembered later when I was driving home from my son's game while I had his trophy that everybody gets, of course. It's like, well, wait a minute, the potential energy to spring doesn't change. So the kinetic energy of only the cart, not the block, and the spring is 1/4 as much because the cart only has 1/4 of the total mass. But the spring still has all the energy. And this is the part where I probably want to try and get some kind of a straight edge in order to draw this, because I want to do a good job of drawing. Yeah, okay, like that. And then there's nothing to explain. It's just a wasted piece of space here. All right. Oh, that's it. Okay, well, that was the end of that. Okay, students conduct an experiment to determine the acceleration of a cart. Cart's released from rest, the top of the ramp. Time t equals 0 moves down the ramp. The x-axis is defined to be parallel to the ramp with an origin at the top, as shown in the figure. Students collect the data, position time, indicate which quantities should be graphed. Okay, well, d and t squared. I've done this so many times with my students. So any of you students out there who are listening, if you seriously didn't do this, or if you overthought, you're like, it can't be d and t squared. I mean, we did that so many times in class. It just can't be that easy. Yes, yes, it could be that easy, you moron. Okay, why did you screw this up? I had students seriously come to me. They're like, "Hey, if you're given a bunch of distances and time script," this is after the AP exam, right? And yes, they were talking to me about the AP exam content, and no, I didn't know I was talking to them about it until after they asked me the question. Like, if you're given a bunch of distances and times, do you do distance and time squared? I'm like, yeah, we did that 8,000 times freaking class. Okay, so what I just did here is I put the distances, the times into here and the distances into here. So then, um, uh, you may use remaining columns in the table as needed to record any quantities, including units that are not already in the table. So time squared, which is in seconds squared, right? It did say including units. Okay, so I'm just going to kind of copy off my calculator here. So 0.15, 0.35. I don't know. I think I'm supposed to use the same number of significant figures, aren't I? 0.59, 0.92, and 1.44, or decimal place, whatever kind of thing. I don't know. I'm not a chemist. I'm not a significant figures Nazi. Okay, so I have a distance in meters. I'm going to have a time squared in seconds squared. Okay, don't want to do this at an angle. I don't want it to look like Battlefield Earth here. Okay. All right. So, all right. Well, 1, 2, 3, 4, 5, 6. Okay, so that's obviously going to be point 0.1, point 0.2, point 0.3, point 0.4, point 0.5, and point 0.6. 1, 2, 3, 4, 5, 6, 7, 8. So how about 0.22468 1 1. So this will be 1.4 and this will be 1.6. Okay, 1.2, 1.0, 0.8, 0.6, 0.4, and then a goose egg right there. All right. So let's see. So I'm supposed to graph 0.6 in the vertical and 1.5 is about right there. Okay, yeah, there's 5 vertically, but there's 4 divisions horizontally. It's so weird. Why would you do it that way? Okay, all right, so 0.14. I'm so slow at graphing. I'm sorry. I'm sorry if I'm boring you. I mean, it's still more entertaining than anything you see on AP Classroom. All right, so let's see here. You're going to get that. There's a 0.5. No, that's close enough for government work. Okay, so there's a 0.92. This is about right there, maybe. And then a 37, maybe right like so. And then 1.44 is probably going to be really close to this line. And I have 0.55. It's about right there, maybe. Okay. So now let's see here. I really badly want this to go through the origin, even though I know I'm not supposed to force it to go through the origin. I think I'm going to force it to go through the origin. I'm going to make it go through the origin. Okay, well, whatever. I probably could have done a better job of that. All right. Well, let's use the old Linreg and find out what it thinks the slope should be. Blah, blah, blah. Okay, it thinks the slope should be 0.381. Now, if I was to choose this point and this point, then that would be 1.55 and zero point 0.6. So what's 0.6 divided by 1.55, 0.38, whatever bull crap. Okay, so all good. So 0.38, sure, is good enough for me. Okay, calculate the experimental value for the experiment. So the slope is 0.6 minus 0 over 1.55 minus 0, which is about 3.87. I think is that what it is? No, point. Sorry, 0.387, please. Okay, and this is equal to half of a. Now, how do I know? How did I know all this? How did I know to do distance of time squared and whatever the other thing? The reason why is because the equation distance equals 1/2 at squared, right? So if I say distance over time squared equals 1/2 a, then that means that the d being on the top is the rise, and the t squared being on the bottom is the run, and then this whole side would be then the slope, right? Okay, so that since that's half of a, let's go ahead and like double that. So 0.38 1, I guess I'll use the Linreg times 2. So the acceleration then would be 0.762 meters per second squared or whatever kind of thing. Okay. The students are asked to determine the experimental value for the acceleration due to gravity using their data. What additional quantities the students need to measure the acceleration of gravity? That would be the angle of the incline. Okay. Write an expression for the value of G experimental in terms of A. Okay, so what you have here is you have the cart, right? And then an MG. And you got an MG cosine, I mean to say. Sorry, it's late at night and I was just watching AP Classroom, so I'm a little punchy here. Okay, so force normal. So mg sine theta. So the mg sine theta is the only unbalanced force. The other two cancel. There's no friction, I think it said. So then you just get A equals G sine theta. So G experimental would be A divided by sine theta, you see. Okay, so there you go. All right, is this problem still going? Okay. The students calculate the value of G experimental to be significantly lower than the accepted value of 9.8 meters second squared. What is a physical reason other than friction or air resistance? Well, that's the two scapegoats I always go to, right? Just blame friction, air resistance. Just blame friction, blame air resistance, blame the government. That's what we blame all my problems on. That could lead to a significant difference in the experimentally determined value of G experimental. I don't know. I mean, you took away the two obvious options here. So, and I didn't write this problem, so I don't know what they're getting at here. I mean, a physical reason. So I don't feel like I can just blame the. I don't think I can blame the students. I mean, unless the time was substantially something. I mean, what would you say here? I mean, maybe the students recorded a much higher value of time than they should have. I mean, I don't know. Or they got did they measure a shorter distance than they should have? I'm not entirely sure where you come up with. If you don't have friction or air resistance, it could lead to a significant difference in the experimentally determined value of G experimental. Okay, I guess the other thing I could go for is um, the angle of the incline. So if the G experimental was lower than it should have been, then the sine of the angle, so maybe the measurement of the incline angle theta is higher than the true theta. I have no idea. I mean, both those answers I don't really consider physical reasons. Physical reason be like a law of physics, right? Well, I don't know. Those both hinge on the students screwing up in the lab. I don't know. How the physical reason you identified in part CI would lead to a decrease in expression. I'm going to number these one. I'm going to number that one two. So one, if the measured time is longer than the true time, if I could actually spell tonight. Okay, if the measured time is longer than the true time, then the acceleration equals 1/2 at squared. Excuse me, the distance equal 1/2 at squared. The acceleration would be less, and the G experimental would be less. But if you say for two, uh, if theta is too high, then gravity experiment A over sine theta, then the denominator is too big, and then your G experimental would be less. I don't know. I don't have any really good reason for this. The students want to confirm that the acceleration is the same whether the cart rolls up or down the ramp. The students start the cart at the bottom, give it a quick push, so it rolls up the ramp and momentarily comes to rest. The x-axis still defined, whatever. Okay, on the following graph, sketch position x and velocity v as functions of time t. Okay, so let's get this right. The x is going to decrease and then increase, and that it's going to do parabolically. The velocity is going to be negative, but be slower and slower and slower negative, and faster and faster and faster positive. Straight line. So this is x equals 1 half at squared plus v naught t plus x naught with a positive acceleration, a negative v naught, and a positive v naught. And this is v equals at plus v naught with a negative v naught and a positive a. So it has a negative intercept, and then it goes up like that. Okay. I did write a question that had the same basic setup, and I sent this to the College Board. So I don't know if this is what resulted because it doesn't look very much like the one that I had, or if somebody else just had the same idea. The stupid block and that stupid spring, a stupid surface. Okay, block M naught, spring constant K naught attached to a rod. The rod is attached to a motor so that the rod can rotate at various speeds about its axis. When the rod's not rotating, the block is at rest and the spring is on stretch length L. Okay, so the rod is not rotating. And if the rod is rotating, then, okay, at time t1, the rod is spinning. Block moves at a constant tangential speed, which there's no centripetal speed, so what the hell are we using that adjective for? Okay, that's like an unnecessary adjective because all speeds are tangential, a-hole. Okay, the spring is stretched distance d. At time t2, the rod is spinning as the disc moves is constant. Again, all speeds are tangential, asshole. And the spring is stretched distance d2 for the is true. Great. Okay. All right, so that was a lot of setup right there. On the following dots, blah, 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 blah. Okay, let me make sure I get the directions correct. Okay, so it's going to be a force normal and an mg, and a force normal and an mg, and a force of the spring and a bigger time t2 is going to be a bigger force of the spring. And if you didn't see my mechanics video, good, because I made a lot of mistakes in it. But I did mention that the last time I went to the reading and there was a free body diagram on the question that I read. I did not know this, but when they say that um, oh, it's just I should probably learn how to read these problems. Okay, these questions. Only the block exerted by the spring. Okay, only the force of the block is exerted by the spring. Sorry about that. Okay, so just ignore those other ones there. Okay, okay, so when they say, sorry, this back to my reading story. When they say that the force has to start on and point away from the dot, when they say starting on the dot, they mean it has to actually start on the dot. If it starts and there's a gap between the arrow and the dot, they actually don't take it. Now, we know that the spring force is bigger at time two because the spring is stretched farther. Referencing D1 and D2, describe your reasoning for drawing the arrows the length that you did. Okay, really, the spring is stretched more at t equals t2, so that means there is a stronger spring force, so I drew a longer arrow, you donut. Okay, now don't forget the people who read these problems are not the same as the people who write them, and they probably hate the problem as much as you do, probably more because they have to read tens of thousands of them in an 8-day period. Okay, Is the tangential speed v1 of the block greater than, less than, or equal to tangential speed v2 of the block at time t2? Hmm. I'm I'm coming back to this one. All right, so I swear I will come back to it. Let's see. Consider the scenario where the block travels a circular path where the spring is stretched distance d from the unstretched length. Determine the expression for the magnitude of the net force exerted on the block in terms of all that. Well, it what? I mean, the net force would literally just be kd. Oh, it's a determine, so I can just write the answer. Okay, I'll screw you showing work. Okay, derive. Now this is more difficult. I have to actually show work here. Okay, derive an equation for the tangential speed via the block. Answer in terms of that shit. Okay, so the net force is going to equal ma, a centripetal. The net force is kd, m, and the acceleration is v squared over the r of the circle. Now this is where it gets tricky because it's actually mv squared over the r of the circle. Where's my picture of the circle? Is L plus D. L plus D. See that? So then you can bring this up and bring this down, right? Now I'm going to say, what am I going to say? Oh, I'm going to say KD times L plus D over M is equal to V squared. So V, let's come up here. V equals the square root of KD L plus D over M. Okay, now I cheated by doing the equation part first. So now I'm going to come back to this. Okay, the V2 I think is going to be bigger. Justify your answer without using equations. So I'm going to say this. I'm going to say, well, two things. First, with more stretch distance, the spring exerts more centripetal force. Okay, so there's more centripetal force, which requires greater velocity, or maybe maybe I should say results in greater velocity. More centripetal force results in greater velocity. I'm going to say this. I'm going to say also more stretch results in a larger circle. The velocity must be more to compensate for the bigger circle. Okay, it says don't use equations. Okay, so let me just tell you what I'm thinking about right now. I'm thinking about the equation net force equals m and acceleration is v squared over r. And so the argument I'm trying to make here without using the equation I clearly just wrote is that if you stretch the spring out more, which is the case in what the fuck is it? In case 2, okay, so in case, what was I thinking just now? Okay, the block is more stretched out, so that's more net force. That requires more velocity to compensate. And then I also was thinking, well, this circle's a bigger radius. So if it's a bigger radius, you need more velocity to compensate. Now, I did not actually think of that until after I did this part. So I totally cheated. I did this part first and then went back and wrote this because while I looked at it, it's like, oh, look, the D is more. That's more velocity. Why? Because the net force is more, and the radius, that's the net force, k times the stretch distance, and that's the radius of the circumference, because they both go up. So I totally short circuited this problem, and the people reading it would not even know. They wouldn't know that I did this part first and then went back to part B or part A. And you know what? Screw you all, because that's totally a valid way to approach it. Does your equation for tangential speed agree with your reasoning? Yeah, it does. The way I played it, yes, it does. All right, explain your reasoning. Okay, D is in the numerator, in the numerator twice, no less. Okay, this is in the numerator twice, no less. So increasing the D increases the V by both increasing the force, which is kd, and increasing the circle's radius L plus D. All right, so that's that. A block of unknown mass attached to a long, lightweight string. Ugh. I don't know. Is that a good trade? I mean, it's long, but would you want it to be lightweight? I don't know, guys. What do you think of that? Ladies, what's your opinion on this? It's long, but it's lightweight. Would that be well, I wonder if that's even worth considering. All right, well, whatever. So your block has a long and lightweight string or something like that. It's wrapped several turns around the pulley. All right, please don't pulley on your long lightweight spring. Mounted on a horizontal axis through its center as shown. The pulley is a uniform solid disk mass and radius r, rotational inertia 1/2 mr squared. Remember, all you folks out in physics land, students don't have to memorize these coefficients. They're always going to be given to them if they need it. The pulley can rotate about its center with negligible friction. The string does not slip on the pulley as the block. The string doesn't slip. I don't know. I want my string to slip, okay? Otherwise, it hurts a lot. Okay, so now that we're done talking about your disk here, when the block is released from rest, the block travels toward the ground. The magnitude of the tension force in Ft. Determine the expression for the magnitude of the angular acceleration in terms of that bull crap. So I'm just going to do a good old net torque equals I alpha. Okay, the net torque is R times force tension because there's the R. And there's the force tension. They're at 90 degrees, so the sine can take the day off. The I is 1/2 mr squared alpha. The R can cancel, and you got a 2ft over mr equals alpha. All right, so scenarios 1 and 2 show two different pulleys. In scenario 1, the pulley is the same solid disc referenced in part A. I know my disc is pretty solid sometimes. In scenario 2, the pulley is a hoop and has the same mass and radius as the disc, but has more rotational inertia because it's a hoop. Each pulley has a lightweight string wrapped around it several times. Each pulley is free to rotate. Great, no friction. Pulleys at rest. Both strings are pulled the same constant force Fa. I know, right? I know a lot about pulling on a string. Okay, a long one, but it ain't lightweight. Okay, so for the same time interval, okay, hold on a second. Same force, same time. Okay, pulleys rotate. After time interval, the change in angular momentum. Okay, the change in angular momentum is equal to the change in angular momentum. But the change in rotational kinetic energy for the disk is greater than that of the hoop. Okay, I'm going to write this out. L disk delta is equal to L hoop delta, but delta K disk is greater than delta K hoop. All right, I needed to write that out in math shorthand. Okay. In a clear, coherent paragraph length response, which may include equations or drawings, explain why the change in angular momentum for both pulleys is the same, but the is greater for the disk. Okay, so here's what I'm going to say. I'm gonna first of all, why is the change in angular momentum the same? So angular momentum is changed by the action of a torque, right? According to delta L equals net torque delta time. It's the same time and the same torque for both scenarios. Like, that's a word I know how to spell. I have to actually look up here in order to spell it. The same torque. Why? The net torque is RFA, and the R and the FA are the same. Okay, so the same change in angular momentum. Okay, I hope that I got that across. That's why the angular momentum change is the same. But here's what I'm going to say. Now, there's a couple of ways you could explain the second part. You could say, well, K equals 1/2 I omega squared. So if the disk has less rotational inertia and the same angular momentum, the disk has more angular speed, and I'm going to say since angular speed is squared, okay, since angular speed is squared, then the k for the disk is greater. Now, let me show you with the equation what I mean when I say this. 1/2 I omega squared and L equals I omega. Okay, so now for the disk has less rotational inertia, so it has more omega in order to keep the L the same. Less rotational inertia, but the omega is squared, so that's like having two up arrows. Well, a down arrow and two up arrows means that you have more kinetic energy. Like that's what I'm trying to explain here in words. I don't know if I'm doing a great job of it, but I don't frankly care because I'm not actually taking freaking AP exams and I don't give shit about it. All right, now the other way you can explain this is you can use this equation that does not appear on the formula chart. Work is net torque times delta theta. Work is net torque. It's kind of like work equals net force, really net work, I should say. Net force times delta x. It's the same equation, but with rotation, right? So net work right here, I'm mad as hell and I'm not going to take it anymore. The net work here is net torque delta theta. Now, the net torque is the same, and I explained all that kind of crap up here, so I'm not going to say that again. But the disk is easier to rotate. So in the same time, it rotates more angle. So more work is done on the disk. Okay, so it gains more kinetic energy, and so I really did the disk gains more kinetic energy. Did I say it anywhere else? I'm always trying to not say the word it, and if I say the word it, I just go back and replace. I finish my sentence, but then I replace the word it. Oh, uh, net torque is the same, but the disk is easier to rotate. So in the same time, the disk rotates more delta theta, right? Okay, so remember, it is shit. So don't say the word it. If you do, just finish your sentence and then go back and replace with what it is. Okay, and then I again, like I said, I did have a little look at these um, before I committed to them, and I looked at this one. I said to myself, "Self, you have a lot of children, and many of them you have sold into slavery." And some of them have been conscripted from you without your knowledge or permission. But you've sold many of your children into slavery. And let me just tell you something. When you sell your children into slavery, you tend to forget about them. But which means you don't really necessarily recognize them every time you happen to see them sometime in the future. But I saw this question. I said, you know what? There's only one asshole on planet Earth that could come up with a question like this, and his name is John Frensley. And so I went back and I looked in my files, and sure enough, yes, this is definitely one that of my children that I sold into slavery. So there you go. You can see what the original draft of the question looked like. And what they did is they turned it into a rod with a single ball at the end of it. I guess they just I mean, Hitler could certainly empathize with a rod with a single ball at the end of it, right? Okay. The rod with a ball attached to it is horizontal mounted axle and carefully balanced so that it rests in a position vertically upward from the axle. The center mass of the rod sphere system is indicated with a cross, which you'll see was in my actual original draft there. There it is right there. Oh my gosh, they didn't edit it that much. Hold on. What? Sorry, that's my wife. I don't know if you can hear her in the mic. She said, obviously, if I write these questions, I use them when I with my students to prepare them for the AP exam. I actually don't. It's because I'm embarrassed. Actually, I didn't think they would actually use this question. I didn't think they use any of them actually, and I'm kind of like I'm too embarrassed about them to actually like show them to students or anything. What is that? All right, so now she's like, why is it that I'm telling you all that I wrote this question? Well, I don't know. I guess it's to show off. So am I embarrassed? Am I trying to show off? I guess I'm kind of both. I'm like halfway. Am I half embarrassed about it? I'm halfway trying to show off. I guess if you pull down my pants, I'd have the same opinion, right? It'd be halfway, half embarrassed, half trying to show off, right? Okay, there you go. All right. It rotates clockwise as it goes down. Okay, the student takes a video of the rod rotating from vertically up to vertically down. Figure 2 shows 5 still shots frames from the video. These frames are not equally spaced apart in time. Okay, great. Use the frames of the video shown in figure 2 to answer the following questions. In which frame is the angular acceleration of the rod sphere system the greatest? Well, I'm the asshole that wrote this, so I know the answer. And the answer is frame C. And the reason why is because frame C has the greatest torque. Frame C, since that is where the torque due to gravity is the greatest. Okay, now remember that torque is radius, force, sine of the angle between them. So if you don't mind, let me actually draw on here the force of gravity, the force of gravity, the force of gravity, the force of gravity, and the force of gravity, right? Okay, now let's talk about the R vector. The R vector points from the axis to the point where the force is applied. There's the R, there's the R, there's the R. The R and the MG make a 0-degree angle, a 45-degree angle, a 90-degree angle, a 135-degree angle, and a 180-degree angle. Here's how the sine function works. The sine function is best for 90 degrees because, excuse me, because the sine basically measures how perpendicular two vectors are. So the sine of 0 and 180 is both 0 because these things have no perpendicular to this to them all at all. These two sines are the same, but it's less than 1 because they're not fully perpendicular. And then this one is 100% perpendicular. So there you go. That's where the torque due to gravity is the greatest. And don't forget, torque equals I alpha. So the better the torque you have, the better angular acceleration you have. Now, in which frame is the rotational kinetic energy of the rod sphere system the greatest? Okay, that would be in frame E, right? And that is since that is where the center mass is at the lowest height. What does that mean? That means you have the lowest potential energy, so you have the most kinetic energy. So let's just say what happened to my ruler. I had a ruler here and it's interrupting my flow that I can't find it. Okay, I'm going to use the color puke green here. So we've got baby barf pea puke green right here, and that's going to represent height equals 0. Now let's draw some KU, 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 KU. Okay, so we have 0 potential energy here. And let's say you have like 1, 2, 3, 4 potential energies. It's not exactly like that, but whatever. And you're released from rest. So that means you have a K and another K and another K. And then you have a K like that. Okay, so that's where you have the most kinetic energy. It's where you have the least potential energy. Those are the bar charts of that situation. Okay, the rod sphere system has a mass and length L and the center mass located at a distance 3/4 L from the axle. Derive an expression for the change in kinetic energy of this rod sphere Earth system from the moment shown in frame A to the moment shown in frame E. Okay, so get this and get it good. Okay, where's my barf? Okay, there's my barf color, and here's my ruler. Okay, so right here, this distance is 3/4 of an L. And this distance is 3/4 of an L. Okay. So then that means that the full height change is 6/4 of an L, which I think is 3/2. So the kinetic energy gained is equal to the potential energy lost, and potential energy lost is mg delta y, and the delta y is 3/2 of an L. So the kinetic energy that you're going to gain is mg times 3/2 of an L. And notice, by the way, the misdirection here. They ask you for the change in the kinetic energy, and I did not get the change in the kinetic energy. I got the change in the potential energy. That's a misdirection. So train your students on looking out for that. It's a misdirection, like in magic, right? Like when the lovely assistant's like walking across the stage and her fluid dynamics is going right, and you're watching the fluid dynamics, like you're hypnotized by the fluid dynamics of the lovely assistant, and you don't see that the magician just like slipped the key key into his little lock and got out of the straitjacket. And you didn't see that because you're checking out the fluid dynamics, right? So that's a misdirection, right? Well, in physics, a misdirection is when they ask you for the kinetic energy after, and you're really going to give them the potential energy before because it's the same amount. Or what's the momentum before the collision? Well, screw you. I'm going to give you the momentum after the collision. It's the same fucking momentum anyway. Okay. Briefly explain why the rod and sphere gain kinetic energy even if Earth is not included in the system. Okay, I took one look at this question. Now, I did the mechanics cold. I told you that in that video. Let's see mechanics in the EMAG too, and I made a bunch of mistakes. So I did look at this, and I looked at this part and I said I did not seriously write this part, and I actually did not seriously write this part. They replaced whatever the last part is, which I'm not going to show you because they may use that last part on another question. Now, I hate the College Board and they hate me, but I am not that unscrupulous yet. I am unscrupulous though. Okay, I put the screw and you into unscrupulous, but not enough where I'm going to show you the final part that I wrote, which is a good part, by the way. To this question I sent them in case they want to use it some other time. You don't get to see that, right? It's like the questions on Jeopardy that they never actually reveal, right? They just go back in the hopper. But I did not write this, and I'm sitting here and I'm looking at this, and I'm like, are you seriously asking me this question? Like, what the frick do you want me to say? Do you want me to say, why does the rod and sphere gain kinetic energy, even the Earth not included in the system? Well, because the rod and the sphere are movable objects, um, and movable objects can have kinetic energy. Like I mean, this feels really dumb what I'm saying here. And the rod and the sphere speed up, so they gain kinetic energy. You know, dingus, right? I mean, is that what you wanted to hear? What do you want to hear? I didn't write this, okay? It's not my fault. Okay, I absolve myself of all responsibility. Do they want to hear that the Earth, which exerts external force? I have no idea what they want to hear. Force. I think they know what they want to hear. Of gravity, okay, which exerts an external on the rod sphere system. Perform, probably not a comma I need there. Performs. Oh, wait a minute. I think okay, there's supposed to be a comma here and a comma here. Earth, comma, which exerts an external force of gravity on the rod sphere system, comma, performs positive work on the rod sphere system. So its kinetic energy increases. Like, what the hell do you want me to say? I don't know what I don't know what you want me to say. Oh, my three favorite words. Okay, get me the frick out of this. Okay, I'm going to bed. All right. Well, this has been a presentation of World's Finest Physics, and I guess I'll do the P2 questions when they come out tomorrow. Gonna dread looking at those too. All right. Well, visit findphysics.com and see what neat stuff we've got going on. Bye.